Hello everyone, my name is Yunting Liu. I am from the University of Tennessee, Knoxville. So I'll be presenting this paper, Quasi-Static Time Series Fatigue Simulation for PV Inverter Semiconductors with Long-Term Solar Profile. So solar energy integration requires power electronic inverters to interface with the electric grid. However, the power electronic devices and their passives have shorter lifetime compared to their connected PV panels. So we can use simulation-based aging analysis to evaluate the aging of the inverter semiconductors. This paper proposes a fast semiconductor fatigue simulation approach that can be adapted to grid-level long-term simulations. This is the basic idea of the aging effect analysis. So we use the PV production profile as the input and try to convert it into the semiconductor junction temperature. So in order to convert this PV profile, we need to use the semiconductor electrothermal model. So this is a typical one. However, thinking of the large data set of this PV profile, we need to find a way to accelerate the simulation, especially the part for this junction temperature calculation. In this paper, we use a FFT-based junction temperature calculation method. So we first decompose the PV profile by FFT, and then only select the low frequency harmonics to find the corresponding junction temperature. So this figure shows the power loss recovered from the FFT result. So it shows that using the DC to fourth harmonics is already good enough to capture almost all the characteristics of this waveform. So after we calculate the semiconductor junction temperature, we can use rainflow counting. And this is a typical algorithm for stress analysis to find the thermal stress for the semiconductors. This slide shows the results from the rainfall counting. So this figure is one of the key results. So we can categorize the thermal stress of semiconductors into three groups. The first group refers to the low frequency stress. So in group 1, the cyclone period is typically ranging from a couple of minutes to a day. The group 2 refers to the cycles, thermal cycles with a frequency of 60 Hertz. Group 3 also refers to the thermal cycles with 60 Hertz frequency. The difference between group 2 and 3 is that group 2 is more related to the thermal cycling when the inverter is generating active power, and group 3 is more related to PV idling during the night. Group 1, those low frequency thermal cycling are typically caused by solar irradiance change, for example, the solar angle change, the cloud cover, or temporary bird shading. And this table shows the accumulated fatigue result from these three groups. So it can be seen that group 1 contributes most of the fatigue of the semiconductor. The other two groups contribute relatively small compared to group 1. So these three figures over here are showing the detailed results of how many cycles in each group. In conclusion, this paper presents an FFT-based fatigue simulation for PV inverter semiconductors. The proposed simulation increases the time step from 100 microseconds, which is typically used in conventional Euler method, to 15 minutes, which is the same as the solar profile data time step in this paper. The proposed physics simulation is suitable for long-term evaluation and co-simulation with other quasi-static simulation platforms for power systems.